We'll see how far we get today. Presumably, if we hit slide, I think it's 24, I will go ahead and stop it there, and we can answer whatever questions you may have. I won't lecture any further beyond that because the rest of the material won't show up on the exam. Okay? I think it's slide 24. I just want to readdress this yet again. Make sure you guys memorize everything on this slide. Okay? You need this information to be able to do the balancing of equations. Without it, you're pretty much lost. Okay? So you need to have this information memorized and ready to go. Where we ended yesterday was looking at voltaic cells and started to move into the mathematics behind all of this. So we've gone through and discussed what a voltaic cell was, or a galvanic cell, all the individual pieces, and putting it together. Now what we want to go through and do is that make sure that when we put it together, we actually get electric current. Okay? And the electric current is going to flow in the direction that we want it to. Okay? Ideally, we would be able to predict the amount of current coming out of that, and that's one of the things that we're going to discuss today. How do we predict that number? So one of the things that we'll have to evaluate first off is what are we monitoring? In the process of any of these reactions, we're looking at a flow of electrons. Electrons carry charge. When charged particles move, they generate an energy. Okay? That energy is what we'll use and monitor as far as our voltaic cells go. Okay? That is typically represented in volts. So if you look at your batteries, they usually say how many volts they store, right? Yeah. Okay. What we're looking at in that case is the energy per charge of electrons being transferred in that process. Okay? And so that's where we get this joule per coulomb term. When we're looking at electromotive force, so this becomes an interesting aspect of this. Okay? When we look at chemistry, it's a huge field. Since it's so old, again, we've discussed this before, where you get varying technologies or contributions to the overall field from differing groups, okay, both around the world and maybe even within countries. Okay? Because of that, a lot of the standard conventions, the signs that we associate with individual things, are dependent on the original discoverer of that material. So when we looked at thermodynamics, we looked at delta H being less than 0 for a good reaction, or delta G being less than 0 for a good reaction. We use that information to derive that entropy should be positive. Okay, so we get lots of possible negatives and positives with that. And we could kind of see where that came from when we looked at the energy diagram, which is what thermodynamics was really trying to develop, was that energy diagram. When we get into electrochemistry, we're looking at a reaction that occurs spontaneously. We want that reaction to occur. Okay? So we're looking at a spontaneous process. We would be considering or thinking something along the lines of delta G, a Gibbs free energy, because that's ultimately what's happening. We're looking at that transfer of energy, which would suggest that we might expect a cell potential to be what sign? A good cell potential. If we go back to our Gibbs free energy, we might expect it to be negative. As we talked about yesterday, what is the sign on a good cell potential? Positive. Okay, why? Ultimately, that charge or that sign was something that was created by convention by the original people that dealt with this information. Okay? It might also fall out of the mathematics, but I'm pretty sure that all we're doing is forcing a sign in there so that we can get these two theories to communicate with each other. Okay? So when you're looking at cell potentials, we will see how they're related to the Gibbs free energy later today. We're going to delay from that a little bit, but remember what we're looking for is a positive cell potential. So when we look at an overall reaction, for that reaction to occur, we need a positive. Okay? So one of the things that we could look at for determining the cell potential for an individual reaction is looking at both the redox or the oxidation cell potential and the reduction cell potential. Okay? And we have to look at both for an individual reaction to occur. Okay? Why can we not look at just a reduction cell potential? See, do I have something on there? If we looked at that table, you guys remember the reduction potentials table that we looked at a little while ago, where we had the positive cell potentials, and we said those were really likely to be reduced. If we took just one of those positive cell potentials and just left it on its own, would we expect that reaction to occur? So we're looking at a reduction, so what, a gain of electrons. So if we took, say fluorine, and we wanted to take it to fluoride ion, this had a really positive cell potential, I believe, didn't it? If I remember somewhere, our cell potential for this, our E reduction was something like positive 3 something, 3.46, let's say. Okay, and one of the things that we discussed is that this is a very likely process. Okay, it's a good process. We would expect fluorine to reduce to fluoride ion because of that positive cell potential. But if I took just fluorine, okay, and left it by itself, would we expect it to turn into fluoride? No, why not? Fluorine to fluoride. If I took just fluorine, put it into a bottle, okay, it really wants to reduce to fluoride. Would I expect it to reduce on its own? No, why not? The electrons. For this reduction to occur, I don't need just fluorine. What else do I need? I need the 2 electrons. So while this reaction is very likely to occur once I get both reagents, just putting fluorine by itself doesn't mean it's going to automatically reduce. Okay? It has to be partnered with something. What's that something it would need to be partnered with? Okay? A reducing agent, or something that would be oxidized. That piece needs to give up electrons so that fluorine now has the electrons to transfer across to the fluoride. So when we're looking at our redox reactions, we can look at their likelihood to be reduced or oxidized, but until we partner them with its opposite, we do not see the reaction. Okay? We have to have both reduction and oxidation occur. What's the explanation for why we need both for the reaction to occur? How stable are individual electrons? Not stable at all. So I can't get a source of electrons to just react with fluorine to make fluoride. Okay? Because I can't get electrons by themselves to be able to do that reaction. I have to have an immediate source of them. That source would have to come from some species that is oxidized. Okay? Does that kind of make sense? So the reactions are inextricably linked. You have to run them together. Okay? So what we'd be looking at is trying to determine the cell potential. So if we take our 2 reactions, an oxidized reaction and a reduced reaction, and we want to determine if they do actually react with each other, we can look at the addition of those cell potentials and determine the addition of the redox or the oxidation and reduction potentials to determine the cell potential, which is ultimately the likelihood that that reaction occurs. Okay? Does it occur spontaneously or not? Okay? So we would add those 2 together, and if we got a positive value, yes, it's a spontaneous reaction. If we add them together and we get a negative value, what does that mean? That reaction would not occur as we've got it drawn. Okay? So as far as solving problems, okay, this is kind of a non-textbook way to address it, by the way. We'll look at the textbook way in a second. Okay? We could go through and look up the cell potentials for each of these reactions. Okay? First off, zinc ion to zinc metal. What happened? Oxidized or reduced? Well, I say reduced with red, right? What happened to go from copper ion to copper metal? Reduced. Okay, so what I've done here is evaluated what we would pull directly off the reduction potential, or off of our standard potential list. Okay? If we want to know the cell potential at standard conditions for zinc reacting with copper, we need to add these 2 reduction potential equations in an appropriate fashion that zinc does react with copper. If we just add them right now, as shown, what reacts with what? When you add two equations, what happens to your reactants? Okay, I want to make one new equation. Here's my reaction arrow. What are my reactants? 4 electrons, good. What else? Zinc ion, copper ion. And our products would be zinc solid plus copper solid. Adding two reactions, like Hess's law, right? You understand what I'm talking about now? I'm hoping it's just the morning. Okay. This overall reaction, does that match what the question asked for? Question asked for zinc solid reacting with copper ion. Does it match? No. So what do we have to do? We need to change one of these equations to make sure that that reaction occurs as the question is asking. So what do we have to do? Say that a little bit louder. Okay, we can flip. Here, let's do blue. We can flip our zinc reaction and make it an oxidation. If we do that, that becomes zinc going to zinc ion plus 2 electrons. Our copper would still be 2 electrons plus copper ion goes to copper solid. When we add those two reactions together, what do we get? Zinc plus copper ion goes to copper solid and zinc ion. What happens to our electrons? They cancel out because they're on opposite sides of the equation. Does this equation match what the question's asking? Yes, zinc metal or zinc solid reacts with copper ion. Okay? If we want the cell potential, we need to know what the individual cell potentials for each of these reactions are. Okay, so we could write our cell potential there. Might as well color code. And our cell potential down here. What's our blue cell potential? So for our zinc, why is it positive 0.76? Because we flipped the reaction. So when we go through and flip things, all we're going to do is switch the cell potential sign. So our cell potential for our zinc becomes positive 0.76. What's the cell potential for our copper? Positive 0.34. What's our overall cell potential? Is this reaction spontaneous? Yes, because we have that positive cell potential. What voltage would we read from a voltmeter? 1.1 volts. Okay? So all we're trying to do is align those equations so that they match the question asked to give us the answer. What if I had said, I want to know the cell potential when I react zinc ion with copper solid? So let's go back a little bit here. Let's switch this up. What's the cell potential for now zinc ion reacting with copper solid? What would our equations be? We'd have to flip the second one, so we're looking at zinc plus 2 plus our 2 electrons goes to zinc solid. And we'd have copper metal going to copper plus 2 electrons. Yes? We would add those two up, and in theory when we do that, we see zinc plus 2 plus copper It's exactly what the question asked for. Zinc plus copper plus 2. We'd go through and look at the cell potentials for each of those reactions. What was the cell potential for our zinc? It'll be negative 0.76. It's the exact same thing as what our standard potential shows. It happens to be negative. What happens when we look at our copper cell potential? We flipped that one, so it's negative 0.34, right? What's the cell potential for the reaction? Negative 1.1 volts. Is this reaction spontaneous? No. Which version, or I don't want to ask, how can we make that reaction spontaneous? Okay, for instance, let's pull back to the material we've already seen. In theory, this is an equilibrium reaction. Which direction of that reaction is spontaneous? Left to right, right to left? Right to left. Okay? So if we just redrew our reaction flipped, we'd now have the correct alignment. Okay? Kind of makes sense? Oh, that's not buttoned. Questions about that? Yes?
Do you know if goes right to left because it's negative?
Yes.
Okay.
And what would happen if we flipped it?
Okay.
If we flipped the reaction, took our products and made them reactants, what happens to the sign on our cell potential?
Positive.
Changes sign. So it becomes positive. We now know that that's a spontaneous reaction. Okay? And we go through and we end up with that same result if we looked at all those things broken down. Okay? Yes? What's the question say? In the previous example, trying to decide what, so that's a valid question, and that was asked already, or asked earlier this morning. How do you decide what equation you're using? Some metal ions go to different charge states. How do you decide which charge state is being referred to? It needs to be clearly specified within the problem. Okay? This one wasn't as clearly specified. Ways that you could identify that, you'd see it in your homework where it's clearly specified which one is happening. You might see it written out, okay, in this kind of format without an actual reaction, or you might see the reaction provided for you. The other way that it could be specified, which is a bit mean, is if you'd go and look at a reduction table provided to you. So on the case of the exam, you'd look at that reduction table. If it only shows copper going to copper plus 2, what do you think the question's referring to? Copper plus 1 or copper plus 2?
Copper plus 2.
Probably just the copper plus 2, because otherwise I didn't give you the information you need to solve the problem. Does that make sense? So yeah, it's again an issue of trying to ask a question as quickly as possible. So this question isn't as full as possible. Does that make sense? Okay. Actually, before we do that, so the way that I tend to approach these is use that reduction information and just flip-flop the signs as necessary so that when I add them up, I get the correct equation that the question is referring to. Okay? That way, when I'm dealing with signs, everything makes sense. I don't have to worry about negatives and positives, because if I switch the equation, I know it has to become positive. I don't have to know anything about anodes or cathodes or any of the above. I just need to know what happens with my cell potentials and the reactions that I've already been working with. Okay? The textbook takes a slightly different spin on this. Okay? So again, in convention, we'll always provide the reduction cell potentials. Okay? The one that I provided to you, and I believe the textbook provides to you, you'll see your positive cell potentials higher on the chart than your lower cell potentials. So it'll always be positive, and as you go down the reduction potentials, it gets negative. That can be switched. Okay? It doesn't always have to go positive up top to negative down below, just so that you're aware. regardless of how it's formatted, the positive value means what in a reduction potential? It's more likely to be reduced. Okay? Doesn't matter if it shows up high or low. We're always looking for that positive sign. Okay? The textbook to determine cell potentials, instead of looking at this oxidation versus reduction, because everything is shown as a reduction potential, they give you a new equation. And they say just pull the reduction potentials out of the chart, and then you incorporate a little minus sign in there. Okay, so we look at the cell potential or a reduction potential for a cathode, and we look at the reduction potential at the anode, and we subtract the two. Why do I not like this format? What if you get it really backwards and you do anode minus cathode? What happened? You get the wrong answer. Okay? So you can use this formula, but you have to make sure that you're subtracting the anode from the cathode reduction potentials. What we went through and calculated in the other format, our oxidation plus our reduction potentials, is the exact same thing. All we've done is incorporated that minus sign in a different position. Okay? Our minus sign came in the flip of the equation. The reason I don't like this formula is I'm not very good at memorizing what happened at the anode and what happened at the cathode. Okay? As much as I might preach red cat and anox, it takes me too long to think through that. I'd rather just flip the equations, balance them out, and make sure it works. Yeah?
With that equation too, because in the book they're both in a reduction state, how do you know which one is the anode and which is the cathode?
So you'd have to go through that process to find out which one was the anode and which one was the cathode. So to use this equation, to me you end up doing everything that you would do in the previous case with an extra interpretation step. So it doesn't make sense to me to go through and use it. Okay? So yes, you can use that one. I want to make sure that you're aware that it exists. All we're doing is adding these cell potentials in various formats. Okay? If you're going to stick with just adding or dealing with your reduction potentials, you must make sure that you include a minus sign in that case, because you're not adding two equations. You're actually subtracting your cell potentials because you're flipping one of them. Okay? So it's up to you. Yes?
Do anodes always have electrons on the product? Right?
What happens at the anode?
Loses electrons.
The anode, if we remember back to our rules, was an ox. What was ox for? What does oxidation mean? Loss of electrons, which means the electrons are on which side of the equation? The product side. Okay. It can be a bit difficult to just look for the electrons. The only place that you'll see the electrons would be in the half reaction. If they give you a balanced overall reaction, it's not easy to see. Okay, because the electrons don't show up there. Okay? We could go through a similar analysis with the cathode. Might as well, because I don't know about you, but I thought that breakdown was kind of helpful. What happens at the cathode? We've got a red cat. What does red stand for? Reduction. We're looking at GR for our reduction. We're looking at a gain of electrons. If we looked at a half reaction, where would our electrons be? On the reactant side. Okay? Kind of makes sense? Okay. What does our standard mean? You'll notice we see that little zero, our not symbol on each of these. What did standard mean? Don't remember? Okay, that's a good question to ask on the exam. 1 atmosphere for all of gases. What else? 25 degrees Celsius. And 1 molar for all solutions. All solids and liquids are technically pure. Hey, that would work as a really good multiple choice question. There were 4 things there. Okay, 4 true answers and 1 false. Okay. So we could write that out in a variety of fashions. We've got that set up there. Okay. So if we go back to the example that we just went through and solved, okay, if I want to know the cell potential at standard conditions for zinc reacting with copper, we could go through and look at the individual reactions. Again, we'd still have to have all of these equations in front of us, and we'd see our reduction potentials. Okay? To get zinc going to zinc ion, that has to happen at the anode, because it's oxidation, loss of electrons. To get copper ion going to copper metal, it has to gain electrons. That's reduction. It has to happen at the cathode. So what does that now mean that we've interpreted all that information? To calculate the cell potential, we take our cathode. That's not negative, is it? That was supposed to be positive. Anybody remember?
Yeah, it's positive.
Should be a positive 0.34, right? Our reduction potential for the zinc was negative though, right? Okay. So we would go through and add it up. Our cathode minus the reduction potential at our anode. So our cathode was a positive 0.34 minus a negative 0.76. What do we get? We still get that positive 1.1 volts, the exact same answer. Okay. Secondary place where this becomes an issue, those signs. A lot of students will mess up putting in those signs appropriately. Okay? So I'm not a fan of that method. If you like it, you can stick with it. Just be careful with your signs. Okay? Back to kind of what you could see on the exam. As far as the mathematics go, all we're doing is adding or subtracting 2 numbers. Or let's just stick with adding. We're adding 2 numbers. Those numbers can either be positive or negative. There's only so many different ways that you can add those numbers up, which means, as far as a multiple choice exam goes, you're going to get all of those possible additions and subtractions. Okay? So you could leave the exam thinking you got everything perfect, but had a very simple mistake. Okay? Please watch out for those simple errors. A change in the sign makes a huge difference. You go from being completely right to completely wrong, and there's no in between. Okay? So when taking this exam, particularly in these kinds of issues, when you're adding your positive and negative values, what I would recommend you do is do the problem once, come up with an answer. Hopefully, later on in the exam, you can come back to it because you'll have it starred saying, hey, this is a positive-negative issue, and redo the problem. Do not check your work. Redo the entire problem. If your answer is the same after redoing it, what does that mean? You were either right or you were so wrong that you were going to be wrong anyway. Okay? So stick with your answer. If you get a different answer, now you've got a problem. I would completely ignore that question. Pick one of them 50-50. If you get lots of time, come back to it later. Okay? And solve for it a 3rd time. Okay? Makes sense? Questions on that? Okay. What about the magnitude of our, yes?
Sorry, I do have a question.
Yep.
On the homework, there was a problem like that. They just said calculate the standard EMF of a cell that uses, say, magnesium going to magnesium 2+, and Cu going to Cu2+.
Yes.
Half cell reaction at 25 degrees Celsius. So they're both, like I said, they're both in the reduction. How do you know which one to flip, which one not to flip?
So by definition, we always want our cell potentials to be what? Positive. So which one should you react with which? It's going to depend on which organization gives you a positive cell potential.
So
That's the answer they're looking
for. So if one's negative, we know to flip that one then to make it a positive?
I can't answer that directly because it depends on the situation between those 2 numbers. So
Yeah, because the question in homework was like different. Because on your question, you'll say when zinc reacts with copper 2.
the other way that that could be phrased is provide the positive cell potential for the reaction involving zinc metal and copper metal. positive cell potential, what we'd be looking at, we could go back to our reduction potentials and see that we've got these two equations. Shoot, this one's already been flipped. I'll go back even further. Do I give just the reduction cell potentials somewhere? Yeah. Okay. So this is what you would be looking at. You go back to these two equations. If I want the positive cell potential, I get to decide which of these equations to flip, because right now they're both reduction. So we could say, okay, let's try flipping zinc first. We flip zinc, what happens when we add our terms? We get a positive cell potential. What happens if we picked copper to flip? We get a negative cell potential. Which one's the correct answer? The first one. Okay? In that circumstance, there would be only one positive value, because there is the possibility that they're both positive. Okay? So if we ask for the positive cell potential, there's only one possible orientation that works. And I would guess that that's what's going to happen with the homework too.
So on an exam, would you ask for the positive cell potential or say zinc reacting with copper?
Both are possibilities. Okay, now we got to make everybody dizzy as I flip through it. Okay. We can go back to the magnitude of our cell potential. So we looked at the magnitude of our reduction potential, and we said the more positive our reduction potential, the more likely it was going to be reduced, okay, or the easier it would be reduced. What about our cell potential? Okay. If we compare it back to water, we're looking at the flow of electrons. Which is going to hurt more? If you stand under a waterfall, it's only 2 feet tall versus 200 feet. Anybody stood under a waterfall that's 200 feet tall? How nice does that feel? Okay. Depending on, I guess, how much you've been lifting that day and how sore you are, it might feel like a massage. In other cases, it feels like tiny little needles stabbing you in the back. Okay. So just because, or one of the things we have to evaluate is the size of that positive potential. The more positive it is, the more energy that we can potentially push out of that, the larger our cell potential. Okay? So the more positive, the better. The more likely that reaction will be spontaneous, the more current we could pull out of that. Okay? So this problem should have definitely been earlier. So let's go ahead and take a look at these. Have you guys try and figure these questions out. Feel free to talk to each other or raise your hand and ask me. We're just ranking these based on reduction and oxidation. We don't even have to worry about cell potentials at this point.